Okay, my pre-cal lovelies, here's your notes for section 1.2. This is analyzing functions, and most of it's based on a graph. I'm going to go back over domain and range, except here we're going to look at a graph instead of the equation. Um, let's see, finding all the intercepts, x and y intercepts, which we've already talked about, evaluating a function, which we've kind of talked about, and describing symmetry, which will be new. I'm not sure if you did in Algebra 2 or not. So let's talk about domain and range. Remember, domain is the values of x for which the function or the graph exists. And here we're going to be looking at graphs. We're not going to be looking at equations, which is what we did in class yesterday. Then there's range, which is the values of y. So what I've got to do is describe all of the x values for which my graph does exist. And so let's look at number 1 here. And the way I do this, if I'm looking at x values, is I drag a vertical line. So I start with the vertical line, and usually I just kind of visualize it. I don't actually draw one, but I'll drag a vertical line across, and as soon as I start touching the graph, so here I am at -4. Ooh, I didn't catch that. Watch the scale here, because each block represents 2, so that's actually -2 right here, 2, 4, 6, 8. So pay attention to the scale. But as I drag across, I'm at -4. I'm not touching my graph. Now I'm at -3. I'm not touching my graph. As I keep moving, I finally start to touch my graph right there at -2. So that's where my domain begins. So my domain, and I'm going to answer this in interval notation. I start at -2, and then I continue to touch my graph. I'm always touching my graph as I keep dragging to the right, touching the graph, and I stop touching the graph when I get to, here I am at about 5. When I get to 6, I quit touching the graph. So my domain goes from -2 to 6, and then we have to decide, am I going to include those endpoints or will I not? Notice at -2, that is a filled-in circle, so I'll put a bracket around -2 because I'm filled in there. When I get to 6, it's an open circle, so we'll put parentheses around 6, and that's our domain. Range, we're going to do the same way, except range, we have to remember that's our y-coordinates. So instead of a vertical line, I'm going to drag a horizontal line up the y-axis. Let's see, that's about horizontal. So I'm going to start dragging this line up the y-axis. And as I do, I make note of when I start to touch my graph. Let's see, I'm not touching, I'm not touching, I'm not touching, and right here when I hit the x-axis is when I start to touch my graph. And I am touching it right over here. There's an open circle here, but I'm touching my graph right there. And remember, range, we're answering with y-coordinates. So right now, I'm at a y-coordinate of 0, and then I keep dragging my line up, and I stop touching my graph. I'm still touching it, still touching, still touching, still touching, still touching, and the top of this little semicircle is at a y-coordinate of 4. So that's where my range ends. And then we need to decide, is it parentheses or brackets? And at y equals 0, I actually do have a point right there. So I'm going to include 0, even though there's an open circle there. I have a point at that y-coordinate of 0, and I do actually have a point, even though it's not bold. My graph does actually exist at a y-coordinate of 4, so we'll include both of them. So there's the domain and range for that one. So kind of went slow through that one. I'm going to pick it up a little bit for the rest of them. So let's look at this one. If I'm going to do the domain of this graph, I'm going to do the domain of this one over here, number 2, go back to vertical line, and I start to drag my vertical line across. Let's see, when do I start touching? I start touching right there at -8. So my domain begins at -8, and I'm going to go ahead and make note that this is going to be a bracket because that is a filled-in point. So my domain begins at an x-coordinate of -8, and then I follow my graph across, so I'm at -8, -6, I'm still touching. But when you get to -4, there's a funny thing going on up there. When you look at -4, I'm going to have to move my line out of the way. At -4, I actually have an open circle, so for a very split second, I'm not touching my graph. So I actually stop my domain at -4, and I'll put a parentheses around that because I don't want to equal it. It was an open circle. But my graph continues right after a -4, so then I'll do union, and then starting again at -4 with parentheses, I'm going to drag my line across, and I'm touching my graph, I'm touching my graph, I'm touching my graph, and I'm always touching my graph at all of these x coordinates. Here I am at 2, my graph exists. So I keep moving at 4, my graph exists. And this one has an arrow on the end, which tells you that this graph will go forever up and it will go forever to the right. So this one actually never ends and we will hit every x-coordinate onto infinity. Okay, so now let's look at range. Range, remember that's y-coordinate, so I got to think with a horizontal line. I'll go horizontal, and I'll drag that horizontal line up, and I start touching my graph right down here. And remember, that's y-coordinates. That's -8. The next one would be -10. So I'm starting at -10, and my graph actually does exist there. So my range starts at -10. Then I'm going to drag up. I'm touching my graph. I'm touching my graph. I'm touching my graph. Here, I'm touching my graph. When I get to like -4, I'm touching my graph all over the place 3 different times. So I'm touching my graph. That's part of the range. I keep going. I keep going. See, here's that open circle, so I'm actually not touching my graph right here, but over here I am. So even at y equals 4, I'm still touching my graph. So I'm always touching my graph, and my graph continues to go up forever. So actually we start at -10, and my graph exists all the way up to infinity on the y-axis, and there's the range. Good, good? All right. Moving on. Let's look at these two real quick. We'll go a little bit faster. So domain. For number 3 here, visualize a vertical line. If I drag a vertical line across, notice this also has arrows. Even though it's extremely steep, this thing is always moving slightly to the left. So it's always going left, which means this is going to hit every single x-coordinate to the left. So I'm going to start at -infinity. And as I go across, as I follow my graph, I hit every x-coordinate. Here I'm at 1, here I'm at 2, and it has a little arrow. That means it's going to continue forever in that direction. So my domain on this one is actually all real numbers, -infinity to infinity. And range is going to do the same thing. If I drag a horizontal line up, I'll look down. My graph is forever going down, which means if I go down to -10, -40, -2 trillion, I'm going to touch my graph. So this thing starts at -infinity on the y-axis. As I move my way up, if I'm thinking horizontal lines, as I keep moving those up, I'm always touching my graph up to infinity. So this one, domain and range, is all real numbers. Okay, number 4 is a tricky one. Domain for this one. Okay, as I drag my vertical line across, I start my graph at an x-coordinate of -4. But that's an open circle. So I'm starting at -4. I'm going to put parentheses there, and then I'm going to drag across. I'm touching my graph, 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 still touching my graph, touching my graph. And then when I get to 2 here, I have open circles up there and down here. So I'm actually not touching my graph at all at 2. So I'm going to have to stop for a second. And then we'll pick back up. Right after 2, my graph continues. So after 2, and then this thing goes forever to the right. So 2, forever to the right. So there's my domain, -4 to 2, and then everything after 2. My range. Again, we're going to use a horizontal line, and this one's going to be kind of funny. Interval notation for this is going to be a little bit tricky, but you'll see why in just a second. As I start moving up, am I touching my graph down here? Am I? Yep. Because this arrow means this graph actually continues forever in the downward direction. So I'm always touching my graph. So -infinity is where my y-coordinates begin. And then I'll follow my graph up, and I quit touching my graph right there. That's the last place I touch my graph, and that's at a y-coordinate of -2, and it's an open circle, so we'll put parentheses there. And now I've got this empty space. I've got a little bit of a gap where I'm not touching my graph at all, which is fine. That's going to happen sometimes. And then I touch my graph right here at a y-coordinate of 6. I have all of these points right around in here where I'm touching my graph. So I'm going to say -infinity to -2, that whole range. And then I'm going to be a little bit weird. I'm going to say and at y equals 6. And I'm not going to use an interval notation for that because it's not a span. Interval notation is used when you go like from one number to a different number. Y equals 6, I just have that one line, horizontal line, where at 6 I'm touching my graph. And then after that y equals 6, as soon as I pass 6, I'm no longer touching my graph. Whoops. So there we go. There's the domain and range. How long? Oh my gosh, I've already spent 10 minutes. Okay, I'll try to pick this up a little bit. X and Y intercepts. X and Y intercepts. These are going to be really easy. We talked about X and Y intercepts from equations earlier. basically you're just going to look at the graphs and tell me where they are. So the x-intercept for number 1. And also make note, x-intercepts, I will usually refer to them as either zeros or roots. It's the exact same thing. Those three phrases, x-intercepts, zeros, roots, are all the same. So my x-intercept, I have 1, and we're just going to have to kind of estimate this one. It's not exactly on a nice number. It's -1, -2, -3 point something. I'm just going to say -3.2 for one x-intercept. And my other x-intercept looks to be at 1, -3.2, and x equals 1. So there are my x-intercepts. My y-intercepts for this one. My y-intercept looks to be at y equals 4. Yeah. All right, moving on. Number 2 here, x-intercept. Where am I touching my x-axis? Let's see, well, I have 2 places, but remember that's an open circle, so I'm not actually touching the x-axis. I am touching right here, and if you watch your scale, that's -2. So an x-intercept at -2. My y-intercept, again, this one we're just going to have to estimate. That looks like 2. This would be about 3. So maybe 3.5. And that's a guess. If you're in that vicinity, I'm okay with it. Now, if you said 4.8, that'd be way off. But 3.5, 3.6, somewhere in that vicinity is okay. So there's intercepts. More intercepts. We know how to do that. I'm just going to skip this for the sake of time. All right. Evaluating functions. If I give you a function, I want you to evaluate it, say f of 5. Now notice this is the graph of f of x. What I've done is I've taken out the x and I've plugged in 5. So basically, I'm just going to go to when x is 5. And I didn't label the axes, so we're going to assume it's by ones. So 1, 2, 3, 4, 5. And at 5, my point is up here. That's actually the ordered pair, 5, 2. So f of 5 is 2. So if it's f of something, the thing inside parentheses represents the x coordinate. So number 2, when is f of 0? That means x equals 0. And f of 0, my graph goes right through here, and that looks like a y coordinate of -1. Number 3, when does f of x equal 1? That's worded a little bit differently. Now, when you see f of x in its entirety, you could think of that as saying when does y equal 1? So when does y equal 1? That basically means find all the points on the graph when the y coordinate is 1. So it starts right here, and this happens at x equals -5, because at -5, my y coordinate is 1. Follow your graph along. Again, at -1, my y coordinate is 1. And then there's one more right here. It's kind of a weird one. We don't know exactly what that is. I'm just going to estimate about 3.5. If you say 3.6 or 3.4, I'm okay with that. When does f of x equal 0? Again, I'm telling you the y coordinate is 0. And my y coordinate is 0 means I'm on the x-axis. So I've got 1 right here. Looks like maybe x equals -0.7. That's a guess. And then another time when I'm on the x-axis is at x equals 3. All right, last one for this one. How many times does f of x equal -1? Now again, that's asking how many times does the y coordinate equal -1. So I'm simply going to count how often I hit a y coordinate of -1. So following along, I'm up here positive y's, positive y's, positive y's, and right here I hit -1. That's a y coordinate of -1, so there's once. And then as I follow my graph, again, I cross y equals -1. So there's a second time. So that looks like 11. It's supposed to be tally marks. All right. So 2 times. Good. I have another problem right here. I'll just leave it here for a second. If you want to try this, I'm not going to go over it. You can ask me in class tomorrow. I'm going to omit this just for the sake of saving some time. So there's another problem if y'all want to give that one a shot. All right, moving on. And then the last part is symmetry, and I'll see if I can knock this out in about 5 minutes. Symmetry is really easy if you're looking at graphs. We have 3 different types of symmetry. We have y-axis, which we will refer to as even, origin symmetry, which is odd, and x-axis symmetry, which doesn't have a cute name. So let's see. Y-axis symmetry simply means the graph reflects across the y-axis, and here's an example of it. If you look to the right of the y-axis and the left of the y-axis, it's the same thing. It's almost like we could fold it over the y-axis. So this is what y-axis symmetry looks like. And if you have a graph, it's really easy to tell that. When it gets a little bit trickier is when I don't give you the graph and I give you an equation. So we need to determine whether or not these have y-axis symmetry, and the way you test that is right here. You plug in negative x for x, and you hope to get the same function back. So if this is f of x, I'm going to do f of negative x, which means everywhere I see an x up here, I'm going to pull the x out, and I'm going to plug in negative x, and then we clean that up. So the square root I'm not going to mess with. Okay, if you square negatives, it becomes positive. So negative x all squared becomes just x squared. The 6 was not affected. And after I plugged in negative x, I cleaned it up. I actually did not change the equation. This thing is the exact same as the equation I started with. So this is the same as f of x. When I plugged in negative x, I got my original function back. Therefore, that's the symbol for therefore. If you didn't know that, this has y-axis symmetry, which we will call even. Y-axis symmetry is an even function. Here's another one. F of x is that stuff. If I plug in negative x, I'll take out the x's, negative x to the 4th, plus 3 times negative x to the 2th, minus 2. And if you clean that up, a negative to an even power will turn positive, plus a negative to an even power that remains positive, and minus 2 isn't affected. And you notice after I plug in negative x, I got my original function back. So this is the same thing as f of x. Therefore, this is an even function. It has y-axis symmetry. So there's your algebra test for an even function, or for y-axis. Origin symmetry, a little bit harder to see, but origin symmetry means you could rotate the graph 180 degrees and it doesn't change. And I can do this here. I can simply grab this. If I turn this graph upside down, you'll notice it doesn't change. It looks the exact same as it did when it was right side up. That is origin symmetry. If you can rotate it and it doesn't change, that's origin symmetry. If you're looking at an equation, the good thing about the test is it starts the same way as an even function. So the test for even and odd is pretty much the same. You just get a different result. So if I were to plug in negative x, I get negative x all cubed minus a negative x. So I'm plugging negative x in for my x's, and we clean that up. If you cube a negative, raise a negative to an odd power, it will remain negative. Minus a negative x will be plus an x. And if you look at this, you'll notice that I almost got the same function back, except it's exact opposite. So negative x cubed plus x, that was positive x minus x. This is the opposite of my original function, and that makes this an odd function. And remember, odd and origin are interchangeable. Okay. Let's test this one. I'll plug in negative x. Let's see, I'll take out that x and I'll plug in negative x. I'll take out this x and I'll plug in negative x. And we clean that up. Okay, my top, I can't really do anything to that. It's just negative x over the bottom, that's x squared plus 5. And this one, if you notice, my top changed, but my bottom remained the same. That actually is the same thing as, and you can take that negative and you can actually move it down in front of the whole fraction and turn this into negative x over x squared plus 5. And what I did right there is basically the same thing as saying negative 1 divided by 2 is the same thing as negative 1/2. I just took the negative off the numerator and stuck it in front. And this is the opposite of the original fraction, which means this one is also odd. Whoops, forgot to go. Good? How am I doing on time? Oh, goodness. Let's see, so that's origin symmetry. And the last one, and this is extremely rare, is a blank page. Ah! Okay, here we go. X-axis symmetry, very rare. It doesn't have a cute name, but it's kind of like y-axis except x-axis. If you look above and below the x-axis, you should have the same thing, just mirrored. And the reason this is so rare is because something that has x-axis symmetry fails the vertical line test. It's not a function. And most of what we deal with in pre-cal and calculus and maths are functions. So you don't see this very much because it's not a function. But that is a graph of x-axis symmetry. And the test is a lot like the other tests, except for x-axis symmetry. you plug in negative for the y. You don't plug it in for the x. So you replace the y's with a negative y, and if the equation doesn't change, you have x-axis symmetry. So I'll take out my y, plug in negative y, and we'll clean that up. Negative y squared is y squared minus 4, and notice my equation didn't change. They are the same. That means this has x-axis symmetry. If you plug in negative y for the y, and it doesn't change, you have x-axis symmetry. One more and then we'll quit. This one, remember you don't touch the x's. We're going to leave the x alone, but we take out the y and we plug in negative y, and we clean that up. So x squared, negative y squared is y squared. It stays positive, equals 9. And notice again, my equation did not change. Therefore, this one is also odd. And that's all I'm going to do. There is this last page. Let me go back. Did I leave that page too quickly? All right, there we go. There is this last page. I was going to work these problems out just to test the symmetry. If y'all want to work these out, you can pause this. I'm about to give you the answers in about 5 seconds. Work these out if you want to. The answers are, if you pause it if you don't want spoilers, this one actually has no symmetry. Number 1 doesn't have any symmetry, which happens a lot of the time. It fails every test. Number 2 ends up being even, which is also known as y-axis symmetry. And number 3 ends up having x-axis symmetry. So there we go. 21 minutes. I've got to learn to get these a little bit faster. All right, I'll see you in class Thursday. Take care.